The arithmetic micro-operations can be implemented in one composite arithmetic circuit. The basic component of an arithmetic circuit is the parallel adder. By controlling the data inputs to the adder, it is possible to obtain different types of arithmetic operations. The diagram of a 4-bit arithmetic circuit is shown here. It has 4 full adder circuits that constitute the 4-bit adder and 4 multiplexers for choosing different operations. There are two 4-bit inputs A and B and a 4-bit output D. The 4 inputs from A go directly to the X inputs of the binary adder. Each of the 4 inputs from B are connected to the data inputs of the multiplexers. The multiplexer's data inputs also receive the complement of B. The other two data inputs are connected to logic 0 and logic 1. Logic 0 is a fixed voltage value, 0 volts for TTL integrated circuits, and the logic 1 signal can be generated through an inverter whose input is 0. The 4 multiplexers are controlled by two selection inputs S1 and S0. The input carry Cn goes to the carry output input of the full adder. The input carry Cn goes to the carry input of the full adder in the least significant position. The other carries connected from one stage to the next. The output of the binary adder is calculated by the following arithmetic sum: D is equals to A plus Y plus Cn, where A is the 4-bit binary number at the X inputs and Y is the 4-bit binary number at the Y inputs of the binary adder. Cn is the input carry, which can be equal to 0 or 1. We note that the symbol plus in the equation above denotes an arithmetic plus. By controlling the value of Y with the two selection inputs S1 and S0 and making Cn equal to 0 or 1, it is possible to generate the 8 arithmetic micro operations. When S1 S0 is equals to 0 0, the value of B is applied to the Y inputs of the adder. If Cn is equals to 0, the output D is equals to A plus B. If Cn is equals to 1, output D is equals to A plus B plus 1. Both cases perform and add micro operations with or without adding the input carry. When S1 S0 is equals to 0 1, the complement of B is applied to the Y inputs of the adder. If Cn is equals to 1, then D is equals to A plus B bar plus 1. This produces A plus the 2's complement of B, which is equivalent to a subtraction of A minus B. When Cn is equals to 0, then D is equals to A plus B bar. This is equivalent to a subtract with borrow, that is A minus B minus 1. When S1 S0 is equals to 1 0, the inputs from B are neglected and instead all zeros are inserted into the Y inputs. The output becomes D is equals to A plus 0 plus Cn. This gives D is equals to A when Cn is equals to 0 and D is equals to A plus 1 when Cn is equals to 1. In the first case, we have a direct transfer from input A to output D. In the second case, the value of A is incremented by 1. When S1 S0 is equals to 1 1, all ones are inserted into the Y inputs of the adder to produce the decrement operation D is equals to A minus 1 when Cn is equals to 0. This is because a number with all ones is equal to the 2's complement of 1. The 2's complement of binary 0 0 0 0 1 is 1 1 1 1. Adding a number A to the 2's complement of 1 produces F is equals to A plus 2's complement of 1, which is equals to A minus 1. When Cn is equals to 1, then D is equals to A minus 1 plus 1 is equals to A, which causes a direct transfer from input A to output D. We note here that the micro operation D is equals to A is generated twice, so there are only 7 distinct micro operations in the arithmetic circuit.